Students, now we'll go to the second session. Second session is the continuation of the first session. And of course, we are going to have some practical ideas, experimental ideas that we are going to have. We are going to get the binding energy values of some materials. We are going to have some materials I'm going to introduce now. And these variational calculations are available. That is, we are going to get the energy eigenvalues of some other material, and these packages that we are going to use are all free. They are freely available in the net. Okay, you can download. I will show what are the directions, how to write the program, and you can enjoy the answers. Okay, now before going into the calculations, first we will see what is a variational method, variational approach. And of course, in the session 1, we calculated the energy eigenvalues and the wave function of a Schrodinger equation of a particular Hamiltonian in the exact form. That is, we have obtained we have taken one Hamiltonian, then Schrodinger time independent wave equation, and we have a quadratic equation, and we obtain the energy eigenvalue and wave function. So these are exact solution for exact Schrodinger equation, for exact Hamiltonian. But in this case, variational principle, we are going to guess the wave function. You are going to guess the wave function depending on the situation. Situation means in the, for example, we'll take bulk material. So what we call this a bulk material is nothing but electron will roam around here and there, everywhere in all the directions. There are no restrictions. There are no confinement. We call this as a bulk material. Suppose if I am going to confine one direction, if 3 dimension exists, I am going to confine only one direction. The electron will try to move in a plane because I have restricted one direction. Okay, either Z direction or X direction or Y direction, whatever may be. I have restricted only one direction. So electron will try to move in a plane. We call this as a well problem, quantum well problem. You just take a well, depending on the height of the water, people will swim only on the plane, on the well. Okay, so that's why we named as well, quantum well. Suppose if I am going to restrict on two directions, okay, the electron will try to move in a single direction. We call this as wire, quantum well wire. Suppose if I am going to restrict in all the directions, all the three directions, electron will be restricted in all the three directions. What we call this as dot material, quantum dots. Of course, depending on the situation, we can increase or decrease the size of the dot. So we can say that dot will give us discrete values. Just remember this one. Any quantum dot will give us the answer as discrete energy levels. This is exactly similar to the any atom. Atom also will give us discrete energy levels. So what we call this quantum dot as artificial atom. That is exact atom. Here it is artificial atom because we can reduce or increase the size of the quantum dot. So quantum dot will resemble exactly the atom. Only thing is we can increase or we can change the size of the dot. Okay. Now another very important. So I said already about quantum well wire, quantum dots. They come under, nowadays we call this as nano. So earlier, this is termed as low dimensional semiconductor systems. In physics, 1970s, 80s, 90s and all, at the time we call this as low dimensional semiconductor systems, which give us quantum well, quantum wire and dot. Nowadays, this is termed as a nanomaterial, nanoparticles. Okay, nanophysics. So now, next point in the variational calculations. As I said just now, variation calculations in which you are going to guess the wave function. So there will be a Hamiltonian, of course. There will be a Schrodinger equation, but we cannot have a wave function. Earlier, in the first case, in the approximation method, we discussed about the infinite quantum well problem. At the time, quadratic equation out of which we can have some solution. But here we are going to guess the wave function. How to guess the wave function? We will have to guess the wave function according to the properties which you have already studied in the postulates, under postulates. The main thing is the wave function should disappear at both ends. Wave function should exist only inside the well, inside the wire, inside the dot. Everywhere at the outside, it has to disappear. It has to tunnel through. This is the main idea. For example, just take you would have studied in plus 2. Limit x tends to 0, sin kx by x. Can you remember this? Sin r by r. With limit r tends to 0, sin r by r. What is the answer? The answer is 1. It means limit r tends to 0, sin r by r, the answer is 1. It means there exists some particle. Suppose limit r tends to 0, sin r by r will give you answer as 0. So, so wave function doesn't r by r, sin x by x. So that also we can have 1. You can have a wave function, compare, and we'll have to compare these two wave functions with the exact energy values. And of course, for example, you just take hydrogen atom. Hydrogen atom in which we have one proton and one electron. Of course, we know the binding energy of the electron with the nucleus is given as minus 13.6 electron volt to be know already, correct? So this was calculated in the year 1911 by Niels Bohr. Minus 13.6 electron volt, we know already. Now you are going to guess a wave function, and you are going to obtain one wave function. Say you are going to guess a wave function, you are going to obtain the energy values, and the energy value goes like this: minus 12.5 electron volt. And I am going to guess one wave function, and I am going to obtain a energy eigenvalue. And around minus 12.8 electron volt, 12.5 electron volt. I have guessed one wave function. The answer is minus 12.8 electron volt. What is actual energy? Minus 13.6 electron volt, which is closer. The wave function which I guessed is very closer to minus 13.6. So my wave function which I guessed is more appropriate than you have guessed. So this is what the idea is. One. Second one. See, the wave function that we have obtained different answers that we have obtained, correct? You have guessed one wave function, you have obtained one answer. I guessed another wave function, and I have obtained another answer. These answers are called as upper bound values. These upper bound values will be always greater than that of the true experimental values, which is nothing but minus 13.6 electron volt. It will be greater always, because electron will tend to be in a minimum position. You just remember this word, minimum. Minimum and maximum we always differentiate. To get minimum value, we'll have to differentiate. To get maximum value, we'll have to differentiate with respect to some parameter. These parameters called variational parameters. So you have a function, wave function, in which you have variation parameter or variation parameter in a wave function, doesn't matter. More variation parameters we have, the more accurate answer that we are going to get in. Very important concept in variation method. For example, we are going to apply external perturbation, say magnetic field, electric field. Each field will have a separate variation parameter. Each. So number of variation parameters that you are going to get and you are going to minimize, you will get more accurate answer that you are going to get it. So this answer should be compared with the original answer. Original answer
Hello,
means
sir.
the true energy of the system. That is the exact energy of the system.
Sir, hello.
Yeah, yeah.
Sorry for interruption. Sir, உங்க ஸ்லைடு வந்துட்டு சேஞ்ச் ஆகவில்லை. ஃப்ரீஸ் ஆகி ஸ்லைட் நம்பர்
இல்ல. No. Let it be. This is correct only.
ஓகே சார்.
Still introduction only.
ஓகே சார். ஓகே சார். தேங்க்யூ சார்.
Yeah. The introduction is going on. Sorry. I lot to first இந்த introduction முதல்ல சொல்லிடுறேன். ஸோ இந்த ஸ்லைடுக்கும் அடுத்தடுத்த ஸ்லைடுக்கும் இதுக்கும் சம்மந்தம் இல்லை. ஓகே, இது இன்ட்ரோடக்ஷன் தே ஷுட் நோ, அதுக்காண்டி தான். ஓகே, so we start with now variational calculations in which we are going to guess the wave function. As I said, we are going to guess the wave function and whichever is the value which is closer to the experimental value. Okay, so you have to choose. This is the second point. And third point, this is applicable only for the hydrogenic system. Very important concept. Okay, hydrogens, as I said, hydrogen system in which we have a proton and an electron. Just now I said that this is applicable only for the hydrogenic system, hydrogen like atoms. What is the meaning of hydrogen like atom or hydrogenic system? Whatever may be the system in which you have a single electron, that's called a hydrogenic system. For example, just take silicon doped with phosphor. You leave the hydrogen atom, just leave the concept of hydrogen atom, which is a hydrogen atom, hydrogen system that we know already. Now I'm going to describe about hydrogenic system, hydrogen-like system. Very important one. Just it's a very simple concept. We have silicon doped with phosphor. Okay, silicon has a valence electron of 14. You remember 14. Phosphor has valence electrons of 15. Now I'm going to dope silicon with phosphor. As I said, silicon has valence electrons of 14, as I said. Now, we know already magic numbers, K, L, M, N. So, first orbit in first we will have 2, 8, the remaining 4 will be left out, correct? 2 plus 8 plus 4 for silicon. So, 4 valence electrons are there for silicon. Now, you just take phosphor. Phosphor has, we are going to dope silicon with phosphor. Phosphor has 2, 8 plus 5. So 5 valence electrons are there. Now I am going to dope silicon with the phosphor. Okay. Now 4 electrons of silicon, 5 electrons of phosphor will covalently will bond and will create exact that magic number 8, and remaining 1 electron is left out. Can you remember? Is it okay for you? 2, as I said, 2, 8, then again 1 8 will be there. Below 1 electron is left out. Okay. So this is called a hydrogenic system for a single element. Silicon is a single element. Phosphor is a single element. So now silicon doped with phosphor is a hydrogenic system. We'll go for gallium arsenide. Gallium is the third group material. Arsenide is the fifth group material. 3 plus 5, exact 1. Now I'm going to remove arsenide with another material, and that will give me the same type of 1 electron, single electron is left out, and this can be also used as a hydrogenic system. Okay, so for, as I said earlier, single element, and second one gallium arsenide, binary element, and third one ternary element. 3 elements we are going to have. For example, cadmium, zinc, telluride, anything. So third ternary material, quaternary material, 4 elements, quinary elements, quinary materials. Nowadays quinary materials also available, out of all which the variation principle is used only for the hydrogenic system. Very important concept. Okay, so hydrogenic system, hydrogen like system. So this is used for hydrogen system. Then next, another one is, it can be mostly it can be used to calculate the ground state energy, not for the excited states. Of course, first excited state it's okay. For the next excited state, second and third, we will have more and more error will be there. So this can be used only for the ground state energy. Is it okay? So now, as I said earlier in the introduction, you'll have to find out, you are going to guess the wave function, you are going to get the energy value. We are going to, I'll show all the things how to get the energy values. I'll show. Then another very important, last important one in the introduction is about the packages which are available, softwares which are available. And of course, we know already density functional theory. It's a DFT. It's 2 lakhs 1. Then quantum espresso. Then many softwares are available. And packages, MathCad, MATLAB, Mathematica. So these are all packages. For all one, variation method is the base. If you know variation method well, you can compete all the things easily. Okay. So out of this idea introduction, we are going to look into a small problem which you can do of your own. I have done it 10 years, 15 years before, and I'll show and I'll explain each and everything. Okay. As I said in the introduction about the low dimensional semiconductor systems. Okay. So quantum bells, quantum and materials used for LDSS will be group 3-5. I'll show now, and group 2-6 materials. Group 3-5, I have given the introduction as gallium arsenide, famous materials. We are going to have computation method. We are going to use variational principle. This computation method, you are going to obtain the binding energy value. Okay. The free packages which are available in the net is nothing but MathCad. You type MathCad, it's freely available. You can download and you can use with the help of help. Help will be there at the end. I'll also show how to write, I'll show. Okay. Now, what are the necessaries? What are the applications? It can be used in all efficient electronic and optical properties of low dimensional semiconductor. Nowadays, what we call this as nanophysics. Okay. Earlier, we called this as low dimensional semiconductor systems. So these are all quantum bells. See, quantum bells, as I said, gallium arsenide sandwiched between gallium aluminum arsenide. The pink color is called gallium arsenide. That yellow color is known as gallium aluminum arsenide. X is given, X is a percentage. Okay, it goes from 0 to 1. So gallium arsenide sandwiched between gallium aluminum arsenide, they are all quantum bells. Next one is quantum bell wire. Next one is dot. Okay, I have already told you about restriction, confinement, restriction of directions. If you restrict only one direction, the electron will try to move in a plane, XY plane. So this is called a quantum bell. Restricted in confined in two directions, electron will try to move in a single direction, quantum bell wire. The last one is it will restrict in all the directions, quantum dots. Okay. Now, some of see, look at the elements now. First, third group material. This is very, very famous. See, in the year 1970s, the famous material was silicon. My professor did his PhD only on silicon. So this is a band gap material. It's very difficult to calculate. Of course, the energy will be wasted. Okay, so silicon. Out of all those things, we use silicon material only for our laptops. Still nowadays, but no other way. Okay. Now we'll go for gallium arsenide. Gallium arsenide, we did our PhD and all only in gallium arsenide materials. So gallium arsenide, third group material and fifth group material. You just look at this one, 31 and 33. See, gallium arsenide, third group materials. Third ones, that is in the table. First one, second column and fourth column. Second column and fourth column are combined. So 3-5 materials. Just look at the slide now. BN material, aluminum phosphide, gallium arsenide, indium antimonide. So something like that. So you have BN materials. Even GAP also is available. Gallium phosphide also is available. GAN, gallium nitride material also is available. Okay. So they are all binary materials. Now look at the first column, zinc telluride, and the last one. See, 2-6 materials. Cadmium telluride, zinc sulfide, zinc oxide, famous material. See, zinc oxide, environmental friendly material, zinc oxide material, and mercury with the combinations. HGS also is available. HGSE also is available. HGTE also is available. See, so they are all called binary materials. Only thing is how we are going to choose the material and what is the purpose that you are going to choose the material. So that's very important one. For example, depending on the band gap that you are going to choose, very, very important one, band gap. Band gap is very important. For example, when you take a gallium arsenide, see 1.4 electron volt. Suppose we are going for higher band gap, then we will have to choose some other material. That's all. What is the purpose? What are the applications? That you will have to remember. But the very important thing is you choose those materials which are direct band gap materials, not indirect band gap materials. Indirect band materials are very difficult to calculate. For example, as I said, silicon, germanium, and gallium phosphide, they are all indirect band gap materials. Other are all direct band gap materials, gallium arsenide. Okay. So now we are going to choose only gallium arsenide, which is simplest one, and I'll teach you how to do. Okay, in 10 minutes time. Now, what are the advantages for gallium arsenide material? That is group 3,5 material over group 4,4 material. As I said, 1970s, 70s and all people used only silicon material. After that, they replaced gallium arsenide. Silicon is replaced by gallium arsenide. Nowadays, people use zinc oxide material, gallium nitride material, um, cadmium telluride material for all solar cell applications nowadays. Because of these reasons, gallium arsenide is 6 times higher than electron mobility. It will go very faster. So if it is faster, automatically the operation will be very faster. So that's why we always look at the films and all in a computer very fast nowadays. Your fastest is based on quantum mechanics principles only. For example, we take a cell phone to use it, and wider band gap compared to silicon, and it can withstand higher temperatures. Lot of, say, as I said, direct band gap, and it can be alloyed with ternary and quaternary compositions. Gallium arsenide, see, lattice matched material. See, lattice matched material means, I'll show in a minute about lattice matched material. The lattice constants are equal. When you're going to choose two materials, there should be lattice constant, lattice matched materials. Okay, very important one. Gallium arsenide is brittle, so also a bit expensive. Only thing is gallium is poisonous material. Gallium is poisonous material. So you have to be more careful when you are going to produce or manufacture gallium arsenide. And indium phosphide, indium arsenide, gallium nitride. So those are all some group 3,5 materials. High performance, high efficient optoelectronic devices are available. They are very superior electronic properties, like say electron mobility, direct band gap, low exciton binding energy, of course. And we'll go for 2,6 materials, as I said. Nowadays, people go for 2,6 materials, very, very high efficient materials. So for example, just take zinc oxide material, band gap is very large, environmental friendly material. Only thing is for zinc oxide material, reproducibility is very important. So that concept, zinc oxide material is lagging. When you're going to take gallium nitride material, nowadays all street lights we have only sensors, we have only gallium nitride material because of the reproducibility. Only thing is zinc oxide, of course, it's environmental friendly, and of course, zinc oxide and gallium nitride mineral competitive materials. Both will have almost similar band gap materials. Zinc oxide is environmental friendly material. Gallium is poisonous material. But what of the reproducibility? Reproduce very less for zinc oxide. So some advantages are there, some disadvantages are there. We'll have to use the last in the slide. Last one, DMS material. So dilute magnetic semiconductors. So DMS material is very, very important. When you are going to use your semiconductor, you are going to dope with some magnetic impurities like Mn, or some other uh, magnetic impurities. Fe, you can have. So these Mn materials are impurities, and CDTE, when it is added with Mn, will become CDMNTE, dilute magnetic semiconductors, or diluted magnetic semiconductors. They will become a ferromagnetic material, CDMNTE, and this is used only in the CD disks in the computer nowadays. So in especially it showed some GMR effect. That is, you have a magnetic material, a non-magnetic material sandwiched between magnetic material, or you have a non-magnetic material energy gap Band gap is very, very important. You just look over here. Zinc sulfide has a high band gap, C4 electron volt. AIPE, gallium phosphide. Gallium phosphide, of course, is an indirect band gap material we'll have to avoid. And aluminum phosphide. Zinc's Zn Se, Als, gallium arsenide. See, there's a line here. Aluminum arsenide and GaAs. There's a line here. It is a lattice matched material. You look at the axis, x-axis. It is nearly it's equivalent to 5.65. Okay. So aluminum arsenide and the gallium arsenide material both have 5.65 electron volt. No, sorry, 65 angstrom. See, 5.65 angstrom. It means that they are lattice matched materials. So we'll have to choose aluminum arsenide, gallium arsenide. It will work out. Similarly, we can have a line. For example, just take CDSE and HGSE. See, there's a line, yellow line. So it's a lattice match material. You just take last one, CDTE, INSB, HGTE. So it's a line. Line is there. So they are all lattice match material. So lattice match materials are very, very important when you are going to have. And I'm going to guess a wave function. Somebody can guess another wave function. And these answers that we are going to obtain out of this wave function are called upper bound energies. And these upper bound energies will be always greater than that of the exact energy. Okay, that is E naught. E naught is the exact energy, ground state energy, experimental energy. And why it is greater? As I said, electron will tend to be in a minimum position always. So that's why these energies will be always greater and the true energy will be always lesser or equal. Okay. And what is the very, very important one? We are going to calculate now the procedure to calculate the binding energy. These are things is easily available in the net. You just have it in your mind. Okay. Now H minimum. H minimum is nothing but dH by d alpha. You are going to minimize the wave function. You need not minimize. You need not differentiate. The package will do. Package will differentiate. Okay. I'll show now in a minute. Okay. Now, what is the formula? The binding energy formula is E sub minus H minimum. For bulk material, there is no suborn energy. When you are going to reduce one dimension, quantum well or quantum wire or quantum dot, you will have suborn energy. Don't forget, you will have suborn energy. You will have to subtract the suborn energy with the H minimum. H minimum that we are going to obtain from the variation principle. You are going to subtract because E suborn energy means you have energy without the potential energy. So electron will try to move in a plane, as I said. So that's called a suborn energy. There is no suborn energy for the bulk material. Only for suborn energy exists only for quantum well, quantum wire, and quantum dots. What is the suborn energy for the infinite one? Simple formula is h bar squared k squared by 2m. What is k squared? Pi squared by l squared. Okay. For quantum well problem. For quantum dot, it will be k squared will be 3 pi squared by r. E sub E binding energy equals E sub minus H minimum. Okay. Now normalization, how to go with normalization? Psi star psi d tau. You remember all the formula which you are going to use? You are going to use within a minute now. Kinetic energy to get the in all the calculations we'll have to go with the expectation value. Don't forget. So expectation value of kinetic energy is nothing but kinetic energy divided by normalization. So expression for kinetic energy will be minus h bar square divided by 2m psi star del square psi d tau. Okay, integration divided by your normalization. Now we can use three coordinates. Either you can use Cartesian coordinates for rectangular shape. Spherical polar coordinates, we'll have to use psi as a function of r theta phi. Theta comma phi polar angles. R is the radial part. Theta comma phi spherical harmonics. Theta is a polar angle. Phi is the azimuthal angle. Together we call this as spherical harmonics. Okay. And this is given in the spherical polar coordinates. Suppose if it is a sphere shape, for example, take hydrogen atom. So sphere shape. So you'll have to use only spherical polar coordinates, no other way. So radial part will be your Rn NL. N stands for your principal quantum number. L is the orbital quantum number. So you have RNL square. YLM. YLM is a spherical harmonics. For ground state, YLM answer is 1. R squared sin theta dr d theta d phi. First, we'll take sin theta d theta. Okay, 0 to pi. You have three coordinates, correct? R theta phi. What are the limits? For the first one, R will be 0 to R, capital R, or 0 to infinity. Second, theta will have the limit as 0 to pi. And phi will have limit as 0 to 2 pi. So you'll have to remember, okay? One is 0 to R. R is the radius of the dot. Suppose 0 to L. L is the length of the one side of the dot. Next one is theta 0 to pi. Third one is third coordinate will be phi 0 to 2 pi. You should remember. Now sin theta d theta, when you are going to integrate, that will give you minus cos theta. Limits will be 0 to pi. Then I can substitute. Just interchange and remove the minus sign. Substitute, you will get cos 0 is 1, cos pi is minus 1. So 1 minus of minus 1, that will give you 2. And the next integration 0 to 2 pi d phi, that will give you 2. At the right hand side, you're going to guess the wave function as I said here. Earlier, for the quantum dot, this is impurity. That means, as I said earlier, that wave function is nothing but e power minus alpha r. What is alpha? Alpha is a variation parameter. How to get this alpha value? Alpha value is nothing but inverse of Bohr radius. What is the Bohr radius? We know already 0.53 angstrom for hydrogen atom. For gallium arsenide, suppose we are going to choose gallium arsenide, the Bohr radius, what we call this is effective Bohr radius. Bohr radius we say merely for hydrogen atom. For any other system, gallium arsenide, we call this as effective Bohr radius. Effective Bohr radius for gallium arsenide is nothing but 103 angstrom. So alpha is nothing but 1 divided by 103 angstrom. So this is the idea. E power minus alpha r. Alpha is a variation parameter. We are going to vary this alpha only. Now wave function psi is known. How to calculate norm? Norm is nothing but psi star psi. So we have already calculated. What dr is missing, so dr, we'll have to go with dr here. Okay. Now kinetic energy is formula is, we know already, minus h bar square divided by 2m del square. Now Average value of kinetic energy is del squared sandwiched between psi star and psi. So psi star del squared psi. For spherical polar coordinates, del squared psi is nothing but d squared psi by dr squared plus 2 pi r d psi by dr. You substitute. So that is a complete expression for a kinetic energy. See, kinetic energy 1, KE1. So that is a complete expression for kinetic energy. You have to remember. If you're going on doing something, automatically you'll similarly you can go for potential squared by epsilon naught r. We know already. Of course, we know minus e squared by 4 pi epsilon naught. I have taken CGS units. Okay, both are the same. No worries. So potential energy equal to minus e squared by epsilon naught r. So your potential energy, average potential energy will be sandwiched between your psi star and psi, which is on the right hand side. Okay. Now I'm going to substitute. So potential energy 1 equals 4 pi. I have pulled out minus 1 by epsilon naught. Epsilon naught, of course, dielectric constant for the material that we are going to choose. So minus 1 by epsilon naught 0 to r sin kr by epsilon r. That r, this r will get cancelled by norm. You'll have to divide everything by norm. So total energy, kinetic energy plus potential energy, you are going to minimize with respect to alpha. The computer will do minimize total energy. That is a command. Minimize total energy by with respect to alpha. The computer will get the answer, total energy, and you are going to insert in the next expression. That is EB equals 3 pi squared screen, exactly as it is on the screen. So you can get these slides from your professor. Okay. Differentiation DAF. So something like that. Here you are going to integrate as it is. How we have done on the usually how we will do on the note. We are going to integrate means we are going to integrate. We will write it exactly integration. Here also we are going to use the same symbol integration. That's why I have chosen this Mathematica. For me, it becomes very simple. So that's the reason that I have chosen. Okay, we'll come to the problem. Charge manual or any book, you can get it. And mass of the electron is given as, here we are called this effective mass. Okay, effective mass is nothing but 0.067 mass of the electron. And mass of the electron is given as CGS. Okay, not in SI unit. So 6.1033 in 10 power minus 29. Now the next expression, we are going to convert this one into some units. That is effective Rydberg, effective Bohr radius. See, effective Rydberg, you are going to assume you are going to have the expression as me to the power 4. Can you remember? Me to the power 4 divided by 2 epsilon naught squared h bar squared, which you have already studied in hydrogen atom. Expression for hydrogen atom, this expression is there. Effective Rydberg and effective Bohr radius. Effective Bohr radius, see, on the right hand side you say 5.3 milli electron volt. See, milli electron volt. Similarly, 103 angstrom. See, 102.75 angstrom. As I said earlier, this is effective Bohr radius for the gallium arsenide system. effective Rydberg, effective energy for 5.3 MeV. It means, as I said, you will have the answer for everything. As a good physicist, you should know. For example, 5.3 MeV, it means that you will have the bulk binding energy value for gallium arsenide as 5.3 milli electron volt, and the Bohr radius is 103 angstrom. You should remember. Okay, it's very, very important one, which we'll be using later. Okay, so binding energy for bulk material for gallium arsenide, the value is 5.3 MeV, milli electron volt. Okay, you remember this one. Now we are going to change this value or not. As I said, that we are going to restrict. Can you remember in the introduction? For a quantum dot, we are going to restrict in all the three directions. Okay, can you remember? And we can change the direction, we can change the distance also. That's why this is called as artificial atom. And we are going to change the distance. We are going to change the distance means we are going to change the r value, radius of the dot. Radius of the dot, it can be either 1000 angstrom, it can be 500 angstrom, 400 angstrom, 300 angstrom, 100 angstrom, 90, 80, 70, 60, 50, 40, 30, and 20. Okay, we are going to change. For all the, we are going to reduce the radius of the quantum dot, and we are going to find out the binding energy. This is the idea. Okay. Now your R naught, I'm going to fix it as 20 angstrom. So 20, the computer will have to assign 20 angstrom. Okay. And of course, R equal to R naught by EBR. So R is changed as effective Bohr radius. Earlier, see, look at the previous expression, R naught is 20 angstrom. R is given as 0.1946 is effective Bohr radius for the gallium arsenide for R equals 20 angstrom. And of course, we know that K equals pi by R. Can you remember? Pi by R. Now, psi in means you're going to assume this wave function, sine kr by r e power minus alpha r. And you're going to assign norm. Norm is, can you remember this one? Can you? 4 pi psi star psi d tau. So this is norm. Can you remember? 4 pi psi star psi d tau. D tau stands for r square dr. And of course, we have removed sin theta for 4 pi. So that's why we termed as 4 pi 0 to r psi star psi r square dr. Okay. Now next one. Next one is we are going to have kinetic energy. Look at the kinetic energy. It is not visible. I have written down. Kinetic energy. What is the expression for kinetic energy? Kinetic energy equals 4 pi kinetic energy sandwiched between psi star and psi. Of course, kinetic energy is nothing but minus h bar square divided by 2m del square psi. So psi star del square psi. In the previous slide, I have already shown this one. So psi star del square psi. Correct. For del square psi, we have written as d square psi by dr square plus 2 pi r d psi by dr. I have written exactly. See, d square psi by dr square plus 2 pi r d psi by dr. The computer will do. You just keep one single line there. You just give a command. The package will do. The MathCad package immediately will differentiate. If you are going to differentiate 2 times, immediately you just keep the cursor there with respect to R. You differentiate 2 times. Automatically the package will do 2 times within a minute. So that's the idea behind this MathCad. And potential energy, expression of potential energy will be, as I said earlier, potential energy sandwiched between psi star and psi. So that that expression is given. Okay. Now the total energy, kinetic energy plus potential, you are going to add these two. So total energy is there. See, alpha, I'm going to give one value. This value is called a seed value. Usually will give us 0 0.01, 0 0.001, 0 0.001. So we'll have to give some seed values. This is called the seed values. And minimize. Give the command minimize. Minimize what to minimize? With respect to what? Minimize total energy, total Hamiltonian. With respect to alpha, the answer is 0.4481. And after that, total energy, you are going to calculate total energy. after getting the value of alpha. So that's why that command is there. So total energy is given as 235.2685. Binding energy I have taken as E ionization energy. Okay, so E ionization energy formula is 3 pi by R whole square minus total energy. This formula already we know this one. Can you remember? Subion energy minus H minimum. Earlier we, can you remember? E binding energy equals, see the last one, 3 pi squared R squared minus total energy. We already studied earlier. See, subion energy on the slide number 10. EB equals E sub minus H minimum. So now we have obtained H minimum. The computer itself will do. So E binding energy that we have obtained for 20 angstrom as 546.268. See, so it's very clear that for 20 angstrom, the answer is 546. I have done for other radius also. For 1000 angstrom, it comes around 1.31. Left hand side you have radius 1000 angstrom, 500 angstrom, 100 angstrom, 50 angstrom, 40 angstrom, 30 angstrom, 20 angstrom. They are all radius. Right hand side are Rydberg. In terms of Rydberg, you have to multiply this with 5.3 MeV to get in terms of millielectron volt. Okay, so 1 means 1000 angstrom. Surely you should obtain 1, because for bulk material answer will be 5.3 MeV. We have taken gallium arsenide material. The answer surely it will be 1. Okay, don't forget, for every answer the answer will be 1 for everything, whatever may be the system. Because for example, when you take CDT material, CDT material will have 11 MeV. Okay, and this will have 60 angstrom. So 11 MeV means for 1000 angstrom you will get 1 Rydberg. Answer will be 11 MeV. So 11 MeV, 11 millielectron volt means the binding energy of the electron which binds with the proton. Okay, that will be the answer for bulk material. Okay, for all the other answer, you just look over here. It increases with the radius. That's the idea. It has to increase because you are confining the radius. When you confine the radius, the energy should increase. It's a logic because of the confinement. See, when you have bulk material, the answer is one Rydberg. It comes around 5.3 MeV. Okay, millielectron volt. Now you are going to restrict. You are going to confine all the directions. Confine the quantum dot. When you are going to confine the quantum dot, it becomes 500. Again, you are going to confine. You are reducing the radius. You are going to reduce the distance. It means you are confining. If you are going to confine more and more, energy automatically should increase. No other way, because of the confinement restriction. Now, but pirated. MathCad 15 nowadays, MathCad 15, it's also available. But you can use a simple program in MathCad 8 itself. No other. No, it's a better choice. How to draw the picture? You just get the Origin software. That also it's freely available. Origin lowest software you can get it. You're going to get only, you are going to draw the picture. That's all for two y-axis. That's all. So you have binding energy. Look at the binding energy right hand side, and R will be left hand side. R is the radius. You are going to draw the graph between these two. R average you can use Excel, doesn't matter. But Origin, that will, you can have some software. It is finishing is very clear. Now for different values of radius, you have obtained different values of binding energy. All the three directions. Look at the binding energy. Binding one quantum dot we have done. And next one we are going to see quantum well also. And we can guess for quantum wire. In all the cases, when you are going to restrict and we are going to confine, we are going to reduce the dot radius or well wire radius or well size for the quantum well problem, the binding energy should increase due to the confinement because you are restricting. And this is for the quantum well problem. See, look at this. This is for the quantum well problem. I have done exactly the same calculation. You can copy gallium arsenide material. This is for the quantum well problem. And look over here. I have chosen different wave function. See, here I have taken as a cylindrical coordinate. Earlier I took as a spherical polar coordinates. See, that's the difference between these two. And of course you can do it, doesn't matter. But I want to differentiate. Here I have taken cylindrical polar coordinates. See, rho phi z. Here taken rho phi z. Z goes from minus L by 2 plus L by 2. Rho is 0 to infinity. And of course phi is 2 pi. Okay, 0 to 2 pi as you have seen earlier. That's why we have obtained as 2 pi. So 2 pi minus L by 2 plus L by 2. So as I said earlier, you'll have to be more thorough with the mathematics background. If you are good at mathematics, it's very, very simple for you. Try to learn mathematics. As far as I'm concerned, if you are good at mathematics, usually I'll consider as you are intelligent. So what I can suggest you is you have your own generation. In the next generation, you ask them to learn mathematics earlier itself, in the childhood itself. Try to ask them to learn mathematics very well. Mathematics is the queen of all subjects, not only in physics, all subjects. If you are good at mathematics, you are intelligent. This is what I used to consider. Okay. So L we have taken as 100 angstrom. Similar calculations. We'll have to take 1000 angstrom to 800, 500, 300 angstrom, then go for 200. Then we'll have to go for 100 angstrom. We'll have to be more careful because why should I take 100 angstroms more careful? Because 100 angstrom is effective bore radius for the gallium arsenide, in which there will be some exotic behavior. So what we call this as usually exciton bore radius is for gallium arsenide is 103 angstrom. You will get more efficient property around this angstrom. So this is actually called exciton bore radius. Okay, it's nearby where exotic behavior will occur, and this is what we say. This is nano limit. Nano limit will be different for different materials. It all depends on exciton bore radius of the particular material that you have chosen. It's very important concept. We generally we say that nano limit is 0 to 100 angstrom. Generally we say, but depends on the seen earlier, but this is for cylindrical coordinates. We'll have to use that is for the spherical polar coordinates which we have used for the quantum dots. So here, see, look at the cylindrical expressions for kinetic energy of the cylindrical polar coordinates in polar coordinates. This is nothing but d psi by d rho whole square plus d psi by d z whole square rho d z. Okay, of course d phi we have taken as 2 pi. See, and similarly you can go for potential energy. You add these two, will give you total energy. Minimize, you just give the command that will give you the answer as 1.5. See, look at the seed value alpha. Earlier I gave us 0.01. Can you remember? Now here I have given us 0.01. Suppose if answer doesn't come, you'll just change the seed value 0.001 or 0.00001. You will get the answer. No worries. So total energy we have obtained as 63.40. E ionization is nothing but pi by L whole squared. There it was 3 pi by R whole squared. Can you remember? That is quantum dot. This is for quantum well problem. So pi by L whole squared minus total energy. Your E ionization is nothing but we have obtained as 2.9. 2.9. Okay. 2.9. We have taken L as 100 angstrom. We have obtained as 2.9. Okay, and we have converted. See, E and E binding energy is given as second column. L we have taken as in the first column 1000 angstrom width of the well, 1000 angstrom, 500 angstrom, 100 angstrom, and alpha variation parameter that also it varies. It's a variation parameter, and this is the graph which I have drawn in MathCad itself. MathCad itself we can draw, but we can't have a smooth one. See, look at the trend. It's the same. When you're going to reduce the well size, the binding energy should increase. See, binding energy increases. It's very clear. Binding energy increases. 20 angstrom. See, 20 MeV. And for 100 angstrom, see, 20 MeV. Binding energy will increase. This is for the quantum doll, which I have used in Origin software. The same thing. And okay, if there is any doubt, you just mail me or just consult with me now. Okay, so this is for the quantum well. I have smoothly I have drawn using Origin software. This is also freely available in the net. What are the applications of quantum dots? A lot of applications are there. See, many applications are there nowadays. Use sensors, solar cells, LEDs, dyes, organic dyes, quantum computing, of course, quantum dot systems are available nowadays. It is used in fiber optical communications. Can you remember? As I said in the introduction earlier, fiber optical communications in which the minimum transmission and 1.5 micron. So quantum dots as tiny thermometers also available. Okay. Fiber optic communications, the minimum loss C, as I said, 1.3 and 1.55 micron. Materials are used as indium arsenide, indium phosphide material. They are used in the range of 1.55. For telecommunications, fiber optical telecommunications, it is used. And also it has high mobility, high speed optical devices. Okay, everywhere it is used. So if there is any doubt, you just ask me. So thank you for your kind attention, and you have attended the 2 sessions. Any doubt, you just ask me. You can ask me any questions. These are all available in the net. Okay, in the internet, you just type MathCad, easily you can download, you can do the programs. These the slides are available in your with your sir. You can get everything from him. Okay, anything, you just ask me. Okay, any doubts? We will clarify. You can go for gallium arsenide. How to identify the answers? As I said earlier, you'll have to go with effective bore radius and effective energy. Okay, Rydberg energy. The Rydberg energy that you are going to obtain as for gallium arsenide is 5.3. Similarly, you can substitute for CDTA. That will be around, as I said earlier, 60, 11 MeV. Say for 60 angstrom, 11 MeV. If you have obtained 11 MeV, the answer is correct for CDT. If you obtain 5.3 MeV, the answer is correct for gallium arsenide. That's all. For every material, it differs. Okay. So you will come to know all the answers. The thing is, when you're going to reduce the size, the binding energy should increase. For infinite quantum well, for finite quantum well, for a particular radius, it will increase. Then after that, suddenly there will be a drop. It will decrease. Immediately it will decrease. That drop will occur only exactly at the effective bore radius. That's the idea. You yourself can do it. This is starting point for you. So if you do it, it will be easier for you for your project, any project work, or you can project your these ideas into your PhD ideas also. And almost as I said, for all DFT calculations, any packages, any quantum espresso, whatever may be the software or packages, variational calculation is the principle. That is the base idea. Okay, if you are more thorough with variational calculations, it will be very easier to complete. Okay, so thank you, students. Thank you so much. If there is any doubt or any clarifications, please feel free to ask me. And my best wishes to you all. Okay, for your forthcoming exams and for your CSR exams. Some people will write CSR examinations, and you just try to write in the next semester, third semester, and sometimes you may pass. Depends on how you have put your work, and sometimes you'll have to work hard for your next attempt. Just go for second or third attempt, really you will pass. Okay, thank you so much. If there is any doubt, ask me.
Students interact with the resource person. Session is now open for the discussion. சார் இந்த எஃபெக்டிவ் மாஸ் அப்ராக்சிமேஷன் தியரி இருக்குல்ல சார்,
ஆமா ஆமா
அதை ப்ரொபோஸ் பண்ணவர் வந்து எல்இ பிரஸ்ன்னு சார்.
ஆமா,
அவர் என்ன பண்ணாரு, இப்ப நோபல் லாரெட் கூட இல்ல சார்.
பாருங்க, வெரி குட்.
அவர்
சில
வந்து
சமயத்துல அந்த மாதிரி அமையும். சில சமயத்துல
2008 நாங்க மெட்ராஸ் யூனிவர்சிட்டியும் ஐஐடியும் சேர்ந்து ஒரு நானோ ஸ்கூல் கண்டக்ட் பண்ணோம் சார். அதுல அவர் வந்து ஒன் ஆஃப் த பார்ட்டிசிபென்ட் சார்.
ஓ, வெரி நைஸ், வெரி குட்.
எங்க யூனிவர்சிட்டிக்கு வந்தாரு, எங்க லேபுக்கு வந்திருக்காரு சார். அந்த ஸ்னாப் கூட நான் லேட்டர்ல ஷேர் பண்றேன் சார்.
ப்ளீஸ் ப்ளீஸ்.
அப்ப நான் ரிசர்ச் ஸ்காலரா இருந்ததுனால எனக்கு மட்டும் தான் தெரியுது, எங்க யூனிவர்சிட்டியில யாருக்குமே தெரியல அவர் வந்தது கூட.
Wow. Very good, very nice. Nama, I can give you a lot of examples. For example, just take SN Bose. SN Bose என்ன பண்ணிருக்காரு, நோபல் பிரைஸ் கிடைக்கல. சோமர்ஃபீல்டு பாவம். அவருடைய ஸ்டூடெண்ட்ஸ் எல்லாரும் 3-4 பேர் வாங்கியிருக்காங்க. சோமர்ஃபீல்டு கிடைக்கல. வயசானவர் எவ்வளவோ ட்ரை பண்ணாரு. ஹையஸ்ட் நாமினேஷன் பாத்தீங்கன்னா 84 டைம்ஸ் நாமினேஷன், அவருக்கு கிடைக்கல. பாருங்க, இந்த மாதிரிலாம் எக்ஸாம்பிள்ஸ், ரொம்ப எக்ஸாம்பிள் சொல்லலாம். Yeah.
I think students don't have any questions, sir. Participants, if you have any questions, you may ask now. Otherwise, I am going to close the session. Sir, I think you don't have any questions, sir. We may close the session, sir.